Can you hear me well? Okay. Good afternoon. I hope that you are having a good time in Paris. In this time, I'm going to talk about work developed during past spring by a suggestion of my advisor, and in this case, we are studying my advisor is Markus Schweighofer. In this case, we are studying the relation between one relaxation of rigidly convex sets that he introduced, and the operation, this operation described here, that transforms a real zero polynomial or hyperbolic polynomials, that they are somehow equivalent, into another real zero polynomial. So we are going to study the relation between these two constructions. And first, I am going to introduce shortly what is this relaxation, even though I talked about it several times before, but for the new people. So in this relaxation, use the cubic part of the polynomial that we have. It doesn't have to be real zero, but when it is real zero, it gives something nice. And with this cubic part, it is able to produce a linear matrix inequality that verifies that the innermost oval of this linear matrix inequality contains the innermost oval of the polynomial P when this polynomial is real zero. By the way, a polynomial is real zero whenever it verifies that when you restrict it to a line through the origin, all the roots of this restriction is a polynomial in one variable, are real. So to introduce this definition, this relaxation, we have to define the logarithm of a polynomial. That's you are seeing it there, and then with that we can define linear form on the space of polynomial, defining it on a basis. And with this linear form, we can construct these matrices AK that are going to form the matrix in the linear matrix inequality that define the relaxation. The relaxation is SDP here, and is the set where this linear matrix polynomial is positive semi-definite. This is the spectrahedron associated to P in this case, and then this is what defines the relaxation. So the relaxation verifies that when this linear matrix polynomial is positive definite at the origin, and this so then in some special cases it might be non-definite at the origin, and then this creates a problem. But when it is definite, it is positive semi-definite when P is real zero, and then with P you are going to construct another real zero polynomial. It's the real zero polynomial that you get taking the determinant of this matrix MPD. So we have a process, this one, by which you take in the generic case, you take a real zero polynomial and you construct another real zero polynomial. And then there is another process. There are other processes that do that. And the easiest one is the one described in the title of this presentation. Is the operation that takes a polynomial and is in the title. Is the operation, this operation here takes a polynomial and send it to this polynomial plus a new variable and its Renegade derivative. It will describe later what is the Renegade derivative. Well, basically what you do is that you homogenize the polynomial and you take the derivative with respect to the homogenizing variable. Yes, and then we want to study that. We want to study the relation between this operation and the relaxation in order to see if it improves it or not. We will see that it doesn't improve it. but the proof is very interesting. Yeah, here I describe how you are going to perform this operation. And this is just an introduction because we are going to see what happens in the case when we only have one variable. But this case is the proof of this case is much easier than the proof of the general case. So to prove the one variable case, we can use this proposition that is already in the literature that says that when you have, of course, for every real zero polynomial, we are going to normalize them and take them having one as when we evaluated them at 0, they are 1. We can always do that without loss of generality. Then these polynomials, of course, are going to have this determinantal expression that you are seeing here, and then the operation that we described at the beginning, this operation of taking the polynomial and add the Renegade derivative to it, multiplied by a new variable, has a nice description in terms of determinants. So if you have if you have that p is this determinant, you can construct the image of this polynomial using this easy description, where E is the matrix that is all ones. Well, this is a lemma that is very easy to prove. Yeah, it just says that the trace behaves well with respect to diagonal matrices, and this lemma is important to prove the following thing. The following thing is what we actually want to prove for the general case. So in one variable, when P only has one variable, the set defined by the relaxation coincides with the restriction to the first coordinate of the set defined by the image by the operation that we are studying. That means that it doesn't change at all the relaxation. Okay, now some terminology. So in general, for a polynomial P, we will call R a polynomial R that has one variable more, but that verifies that when we set this variable or set of variables to 0, we get the initial polynomial. This is a polynomial extension, and we are interested in studying the intersection of the relaxation of these polynomial extensions with respect to the initial variables, the variables that were in P. And well, I explained that. So there are, in general, there are nice results that we can get relating the rigidly convex set of the initial polynomial that we began with and the rigidly convex set defined by relaxations or transformations of the relaxation. For example, using eigenvectors of extremal eigenvalues, we can get a similar result. This is, I don't know why this is not easy to see, but well, this proposition says that, and this proposition is not important, but it's just saying that in this case you can get a relation that says that both the borders defined by the relaxation restricted to the space of the original variables and the border of the rigidly convex set of the original polynomial, when we define the new extension using an eigenvector of extremal eigenvalue, that means the highest one if it is positive or the least one if it is negative, they touch and we can compute the points in which they are going to touch. They share some points. But well, now we want to prove the the fact that the relaxation is never improved by this operation, but for more variables in the general case, we are going to do this, and we are going to be able to do this because it is possible to reduce the problem to planes. So we can divide the space in infinitely many planes and do the computation there and check that in each plane, the set is going to be all the time the same. We do it in planes. Someone could say, well, you could analyze it also use line by line, and you could also do that. But we will see in the proof. I don't know if it will be very clear in the presentation why this is the case, that we need at least two variables to be able to work properly with the definition of the relaxation, so we can prove this. We are lucky that in two variables, we have the Helton-Binikoff theorem that says that every real zero polynomial in two variables have a determinant representation, and this will be very helpful. So we begin this by generalizing a result that that Marcus proved in his paper, but he proved it only for orthogonal matrices. In this case, we are going to need this result for matrices that are for arbitrary matrices. And what this says is that we can take, if we take a linear transformation, we can always change the linear transformation in the subindex of the linear form and transport it to the argument. And well, there are also some results that we will use. In this case, says, well, this is actually a special case. You could see it as a special case, that a transformation of the variables can be written in terms of a transformation of the set. So that means that if you have a scalar k multiplying the variable, you can put this scalar out as a fraction, and this works. Okay, so now we are going to work with restrictions. We are going to need restriction to planes, and this is what we introduce here. We introduce it in general. We take a set of vectors in Rn, and then we define the restriction of P to the space defined by those vectors as this polynomial that you are seeing here. This polynomial has degree d, generically, the degree of the initial polynomial, but sometimes it might drop. We will see what we do in this case. So also, we are going to denote the SAP to the part of the relaxation that is contained in the line spanned by the vector A. This is A, by the way, is a vector in Rn also. I didn't say it there. So the degree of the restrictions might drop. We don't want that. So whenever we see a restriction, PA, we always keep the information about the degree of the polynomial, where this restriction comes. So we always have to remember that even though the degree of the restriction might be smaller than d, all the operations involving the degree that we are going to perform on this polynomial are going to be as if that polynomial had degree d. For example, I don't know why you cannot see this, but in the case of the Renegade derivative, can you more or less see what is there?
The first row.
I don't know why it takes this color. Well, in the case of the Renegade derivative, you will let me check if I can do something with this. This is not helpful. So in the case of the Renegade derivative, you will homogenize the polynomial PA, the restriction. So this polynomial PA, you homogenize it dividing by the new variable x0, and then multiplying by x0 to the power of d. Always, even when PA might have a smaller degree, and then you take the derivative. So here with respect to that variable, here you see what is the problem that could happen. If you homogenize with respect to a different degree, then when you change the plane to which you are restricting, you might have completely different polynomials because you are taking derivatives with respect to different exponents. So this is what we want to avoid. This is a lemma that you cannot see either. It's a lemma.
Can I ask you for something?
Yes.
Even if we could see this, I mean, is there maybe? I mean, I know that it's very difficult to do virtually, but I could really use an example of everything that is happening in the in the statement.
Yes, but I don't know if I can write.
Yes,
I'm right. Yes, an example will be helpful. This is really bad. Yeah, I don't think I have time to connect to show the example. So what is if I can write something. No, I cannot. No. No, I cannot write. I am sorry. Yeah, well, I don't know why this is not working. Well, yes, in this lemma that some you can see some of them and the other no. It's okay. So well, this lemma explains us how we can deal with these restrictions, and but you don't have to read it. It's okay. It just says that you can in the same way that that you can take scalars out and in, and then that you can perform some linear transformations that will be helpful later. So I am glad that you can see this one. So now we are going to divide the space a space in several variables into subspaces of less variable. We are going to be interested in the case of planes, but we can do that in any case. So imagine that you have an apple or an orange, your favorite fruit, and you want to describe it. You can cut it by slices through a line passing through the origin, and this is what we are going to do. We are going to take infinitely many planes, and these planes are going to verify the following. When you intersect them, they are going to be the space, the subspace through which we are taking these planes. In this case, it will be the line. If you have an axis, and then you take all the planes, this intersection will be the line and the axis. And of course, every planes, all the planes are different. And for each element of this plane, of this set of planes, we are going to take a transformation, an orthogonal transformation, different on each plane. We are going to index these transformations by the vectors that are on this on each of these planes. Each vector of the space is going to be in a different plane. So this is going to index the transformation. We are going to call the transformation canonical, this set of transformation canonical, when each matrix indexed by the plane in which it acts send this plane to the canonical plane, the plane expand by the space expand by the first canonical vectors. This just says that that we are interested mainly in the case where L equals 2, and where the original the line through which we are going to take the space is the line spanned by the first unit vector. Then our canonical plane is going to be the plane spanned by E1, E2, the first two canonical vectors. Okay. Another thing that we are going to do is that when we have a restriction of a polynomial, we are going to consider that they both have the same number of variables, either augmenting the number of variables of the restriction, adding 0 coefficients if necessary, or augmenting the number of variables of the initial polynomial. This is because for the set A, I allowed that A has more than n different vectors. Then one polynomial can have more variables than the other. You say that we homogenize the number of variables, and this is the main fact. This main fact says that the relaxation through the line spanned by the first unit vector of the polynomial, when you restrict the relaxation to this line, you can describe this as the intersection of all the relaxations of a set of restrictions. So these are restrictions. These are restriction of P to the plane spanned by the first unit vector and another vector, arbitrary vector, and then you take the relaxation in that plane with respect to the line spanned by the first unit vector. And when you take all the intersections, this is going to be equal to the intersection of this of the first unit line with the rigidly convex set. Sorry, with the relaxation defined by P. Well, here there is a description of the proof. To prove this, what we do is to choose a selection of planes that we described before, and of transformation on each plane. And using this, we are able to produce a chain of equivalent conditions that you cannot see, but end up in this fact. Okay. So yeah, at the end we get this condition, and this condition is reachable. This condition is equivalent to the right hand side and to the left hand side, and we do that we do this making some orthogonal transformations in the variable x, and some transformations that are not orthogonal. This is why I needed the generalization of the result that was only available for orthogonal matrices. And this description is the reason why we need two variables. We need a plane because it's just in planes where we can transform coherently the two sides of the identity that we want to prove into this expression here. If you try to work with lines, you don't have enough room to do that. And as a corollary of this result, we get the identity not just for the first canonical vector, but for whichever vector you begin with, whichever A. And this result basically solves our problem when we can express when we can find nice expressions for the relaxation. And this happens when we have a determinantal representation. So now we have to see why the operation sending this operation here, sending a polynomial to itself plus a new variable multiplied by the Renegade derivative, why this operation is nice in terms of determinants and determinantal representations. So in general, we are going to define the polynomial p hat as we are going to need the infinite sum, but well, at some this stops at some point because p has a finite degree, and then after some point it will be 0. And we also define the truncation. The truncation of this sum use at 1 because the truncation is the operation we are interested in. But we need the long one because the long one is the one having a nice determinantal expression. So we have the following: the polynomial. If a polynomial p has a determinantal representation of some size d, d can be of some well, yeah, of d the degree of p. This can always be chosen this way. Then the new polynomial, the polynomial p hat, is the long one. Polynomial p hat has also a determinantal representation, and its determinantal representation is easily obtained from the determinantal representation of p. You just add the term y multiplied by the identity. So then that means that this polynomial is going to behave well in this case. And as we are restricting to planes, we take the special case of planes that, and then we have that every bivariate real zero polynomial. We use Helton-Binikoff here. If we have a bivariate real zero polynomial, then this polynomial has a determinantal representation, and then the operation of taking hat is also a real zero polynomial and has a determinantal representation also. Yes, and we have this relation with the for the relaxations. We can truncate at the cubic part because the relaxation only use the cubic part of the polynomial. So in the notation of Schweighofer, what we get is that the matrix, the set defined by the polynomial p hat is equal to the set defined by this other polynomial that is the truncation at degree 2, because the part that has y with cubic degree is not at all in the case in which we take y equal to 0, because the cubic part of y only appears in the last matrix of the relaxation, or the matrix that multiplies y. This is because of the definition of the relaxation. Of course, then we have all this relation between the different linear forms defined for every polynomial. And this relation implies a particular form of these matrices, of the matrices defined by these polynomials. The form that these matrices have is this one. And you can prove, you see that there is a small k here. And this is the k that you are multiplying the last term by k. But they are also special in the sense that A has some repeat columns and some repeat rows. And then you can prove that the first one is positive semi-definite if and only if the second one is positive semi-definite. And this establishes the identity between the restriction to the first plane, the restriction to the canonical plane, the plane spanned by the first two canonical vectors of p hat and p tilde. P tilde is the one we are interested in. Remember, p tilde is the one we are interested in, but p hat is the one having the nice expression as a determinant in general, because p tilde is not in general is not expressible as a determinant. This happened just in degree. This happens just when we had one variable, but for more variables we have to take p hat. But as we can see here with this identity, it is going to be, we can exchange them. There is no problem. And then what we get is the result for the univariate polynomials, applying so here using what we just saw, we get a completely different proof of the result that we saw for one variable. It's important that we had to use Helton-Minikov a lot. And it is good that we have that. And of course, this corollary is the result. This corollary here is the result that we have that we had for one variable. Now we have it in general. And now we reach the last part, in which we see why the Renegade derivative is not helping, because now we just have to take this result relating the restriction to the first two variables of the relaxation to the relaxation with the restriction of the first two variable of the image by this operation of the polynomial of the initial polynomial, and the expression of the planes of the planes in which we divide the space in the relaxation that we proved in the fact before. Then now we can put things together. We can divide. We can take a restriction of a general polynomial. We take a real zero polynomial, and then we take restriction to a plane of this polynomial. We know that this restriction to a plane through the origin is going to have a determinantal representation. We take it with the first matrix diagonal. We can do that. I think it's nicer to have it like this. Determinantal representation, of course, with all the matrices symmetric. And and then we see that because of the care that we took at the beginning, that restrictions and operations involving the degree of the initial polynomial have to be taken uniformly. That is, we fix the degree of a restriction, even though it might drop. Then this implies well, these are linear operations in this space. This is clear, but this implies also that restriction and taking a Renegade derivative commute. And as the other operations, the operation tilde and hat also to define them, what we are basically doing is taking also Renegade derivatives and then summing. This means that they also commute with that. Then we can augment our vectors whenever we need it, adding 0. And thanks to that good behavior of the operations we define, we are able to exchange the operations that we are performing, and with that we can use the previous fact throw planes, restricting, and then the determinantal representation to obtain the equality in each plane. So we first, here we see that we can first restrict, then take the determinantal representation on this plane, then using these operations, and that they have also a nice determinantal representation related with the one that we had before. Use that to see that in each plane we are going to have that the two polynomials we are interested in produce the same relaxation, or the same relaxation of the rigidly convex set of the polynomial, and then we prove the result, that is that the relaxation with respect to P is equal to the restriction setting the last variable, the additional variable y to 0 of the relaxation with respect to the relaxation of the new polynomial. So it proves that in general, as we saw in the univariate case, this operation does not improve the relaxation. Now the question, Colby, why this is important? Why are we studying this? Well, we know that the relaxation that we are using in some special cases is able to carry all the information of the polynomial that we began with. The problem is that so far when we apply the relaxation in a way that it carries all the information, it produces determinantal representations that are not monic, that are not semi-definite or definite positive at the origin. This is why we cannot solve the generalized Lux conjecture. But our hope is that studying other transformations, sending real zero polynomials to real zero polynomials, and how they affect the relaxation, some of those transformations could improve it and get better approximation of the rigidly convex set, even maybe even the rigidly convex set. And we began with this because this one is one of the easiest transformations, sending up a real zero polynomial to another real zero polynomial in more variables. Having more variables is important because our matrices, the matrices of the relaxation they grow with the variables. When we have more variables, the matrices are bigger, and we know that to solve the generalized Lux conjecture, we need, in general, very big matrices. So the question is, can we prove results like this, or results choosing that the relaxation improves for other transformations between the sets of real zero polynomials in different variables? We know that there are other transformations that behave like this, that sends real zero polynomial to real zero polynomial. But in this case, we were lucky that we co-restrict to planes to prove this thing. In general, with other transformations that we have, we cannot do this. And this is the open question that this led to us at the end. And this is the end of the presentation. I am sorry that some parts were not visible. Thank you.
Thank you.
Any question?
Any questions in the audience here?
Yes.
Don't see any questions, Bernard.
So can you relate what you discussed with the general Lux conjecture?
Yes, as I say, this relaxation.
Maybe you can recall what is this conjecture.
Yeah, well, the generalized Lux conjecture says that a real zero polynomial, as I say, is a polynomial that when you restrict it through a line, has all its roots real. So no complex root. The Lux conjecture say that for two variables, these polynomials, when normalized, say that you write it in zero they are equal to 1. They can be written as a determinant of this way. The determinant of the identity plus x1 some symmetric matrices plus x2 another symmetric matrix. This is the Lux conjecture. This is true. Helton and Vinnikov proved it. And the generalized Lux conjecture says that given a polynomial in more variables, if you can find another factor such that the rigidly convex set of this new factor that is also a real zero polynomial has its border outside the rigidly convex set of the initial polynomial, so that the rigidly convex set of the initial polynomial is contained in the rigidly convex set of the new factor, and this has a determinant representation of this form. This is what the generalized Lux conjecture says. We know that we need a factor because for more variables, for dimensional reasons, you cannot expect to find for all real zero polynomials a determinant representation. And the thing is that this relaxation, when you take, for example, a determinant representation that is not monic, one with a signature matrix instead of the identity matrix, this is not what you want. But if you then complete this polynomial so that the matrices in this determinant representation, you take a bigger polynomial with more variables, so that all these matrices generate the space of all symmetric matrices, and you take the same operations that you do for the relaxation, then you will get a determinant representation of this polynomial. The problem is that this determinant representation is also having a signature matrix as the initial matrix. So we know that the relaxation is able to carry enough information to describe the polynomial, but we don't know if there exists a transformation or a choice, a different choice of the coefficients that will allow us to write this polynomial as a determinant. So this is why the relaxation is interesting.
Okay.
And yes. More questions? Or
More questions?
So maybe I have a question and end the comment. But first, my question is, so from the point, so your result is kind of negative from the point of view of doing Lux conjecture, right? Because you're saying that this operation doesn't really help.
yes.
And so in principle, what you want is not to be able to prove results like this, right?
Yeah, I know.
If you want to do, if you're feeling good about Lux conjecture, right? So does this mean that now that you understood what happens with this operation, does this mean that there are some operations where, like your proof strategy doesn't work, so you will be more optimistic about them improving the relaxation?
Exactly. This
So that's my. Are there operations like this?
yes, because there is you can try to take different real zero polynomials and amalgamate them. That amalgamate means that you take them coinciding in some set of variables, and then you take different sets of variables, and you try to find a real zero polynomial that when restricted to the the set of variables of each polynomial, you get the ones you began with. And this approach is not allowing us to do this, because we were able to prove this negative result because we were able to find determinantal representation, nice determinantal representations for this new extended polynomial. But in the case when we take amalgamations with other polynomials, we don't know if this is possible. And we don't know if it is possible to restrict to a plane. So there are two key ingredients here. First is that we can reduce all the work to planes, and then that in planes this operation behaves well. So this happens with this operation. With others, we don't have that, and this will be the thing to study, to find different operations that transform one real zero polynomial into another one, carrying information about the previous one that can be plugged into the process of the relaxation to produce bigger matrices. We always need bigger matrices because for getting bigger matrices, we need to increase the number of variables, because we know that if we don't get bigger matrices, we are not going to be able to prove it. So this is why we take extensions of the polynomial.
Okay, and now I have a comment. So my comment is, so in your talk, you gave us like 40 lemmas, facts, definitions, and warnings before you got to why you were doing this. So I would invert the process. Please start with why you're doing this, and then you can give us the 40 facts, definitions, and so on. But that's, I mean, I know it's a personal decision, but I would much rather get the why first.
Okay. Thank you.
I do have a questions to one of the lemmas. I think it was lemma 21 or something, when you say that a matrix is positive sum infinite if and only if another matrix is positive sum infinite.
Lemma 21. Yes. This. Yes. This. I remember this. I know what you mean. This is. Yeah. It is about. Yeah, it's this one. This one.
This one. So say if you multiply the diagonal escape times A1. Okay. Yeah, I thought it's.
Well, it's a direct application of Sylvester lemma. This is how I proved it.
Imagine the matrix B is matrix 1, 1, 1, 1. Just 4 ones. It's positive sum infinite. And then the 1 is. No, okay, no, you're right. Okay, it's fine. So
it's not direct. It's easy. Maybe there is a direct proof. But I used the Sylvester method. The Sylvester lemma. A is actually the determinant of A is 0, but you have to check the other minors.
And there's A1 there as well. Oh, okay, that's lots more structure than I expected. Yeah, okay, sure.
And this is what this is the aspect that our matrices have. This is why we know that the relaxation is not improving, because when you compute the matrix with the new row and the new column, you see that they are actually that you get this, and then you are not adding new information.
Yeah, I see. Okay, any question online?
Okay.
No questions.
No.
So thank you for the talk again.
Thanks.
And we will resume at 4 o'clock.